All right. Well, let's go ahead and get started here. Hope you had a nice 3-day weekend. Going over these announcements, you've got an assignment that just became due just now, and that was homework 1. Homework 2 is going to be due a week from today at 11 a.m. Thursday of this week is the Winter Technical Conference, and I'm just curious, how many of you are involved with that or are planning to attend? About half the class. Because I want to accommodate anyone who's interested in attending that, I'm going to post our lecture on Thursday online. And so, you're still responsible for the material, and there's still some really important examples in that lecture, and I encourage you to review it, but we won't have any in-person class meeting on that day. Today we're going to be talking about some empirical methods for calculating the friction factor F so that we don't have to rely on the Moody diagram, and then we're going to discuss a method that determines the required pipe size when you know the head loss that's going to be expected and when you know the required flow rate. So before we get into that material, are there any questions on these announcements or anything from our class meeting on Thursday of last week? Yeah.
Question on 7.4 on the homework. I don't know if you're okay covering that or...
Maybe we should go over it one-on-one after the class. I don't have my homework notes with me right now. Okay. Remember the Moody diagram. That is the approach we've talked about so far for relative roughness and a known Reynolds number, how you know what the friction factor is going to be. And of course, one of the reasons why we like the Darcy-Weisbach equation is that the empirical friction factor is dependent on the flow conditions. And it only makes sense because we know that the boundary layer thickness changes as the flow rate varies. It only makes sense that the amount of shear stress that's being applied by the pipe on the water is going to change as the flow rate goes up and down. And so the Hazen-Williams equation is all well and good. It's very convenient. It's very simple, but it's just not realistic that the friction factors wouldn't change. So the Darcy-Weisbach equation does account for variable friction factors, but so far you've been kind of limited to using this figure for calculating the F value. And that it can be inconvenient if you have a solution that has to be solved over and over again because maybe you're making design changes, or it could be an iterative solution where you don't yet know what the flow conditions are. So the Moody diagram can be replaced by the Colebrook equation as one of our methods for calculating the friction factor. Now I guess before we talk about the Colebrook equation, I will point out that this very simple formula for the friction factor when you've got laminar flow conditions, that F is 64 divided by the Reynolds number. That very rarely applies because we've already talked about how infrequently flow will be laminar. In a pipe network, it would maybe only be seen during the very low periods, low demand, like in the middle of the night when there's hardly any water being used in a network. And so in that case, it's conceivable that you might be able to use this laminar flow friction factor, but more often our Reynolds number is above 2,000. And so the Colebrook equation is what applies. Now you can see here in the Colebrook equation that it's relatively complex. And one of the challenges of solving it is that what we're trying to solve for, remember, is F, the friction factor. And that unknown is on both sides of the equation. And it can't be isolated algebraically. It's going to stay on both sides of the equation. And that's what we call an implicit equation. It's an equation where the unknown is on both sides, and so we have to solve it iteratively with a variety of guesses for F. And then eventually when the left-hand side of the equation is equal to the right-hand side of the equation, then that's what tells us that we've got the correct value for F. So we'll get some experience using that approach today just to practice the Colebrook equation. It's very accurate. It's valid over the entire range of flow conditions that you'll see. It's valid for the entire range of relative roughnesses that you'll see. Remember here that the K sub s value that we're seeing in the equation here, depending on the text, sometimes it's labeled as, say, K sub s, sometimes the variable is epsilon, but what it is an equivalent sand roughness, and that's where they've looked at the roughness, the average roughness for a certain pipe material, and then they're expressing it in terms of an equivalent sand diameter and what that sand diameter would be. So the two components of the Colebrook equation inside that logarithm, the two factors that affect F value, first of all is the relative roughness of the pipe, and so K sub s divided by 3.7d. And then the other factor is the flow conditions. And so the Reynolds number is in the denominator of that second term. And if we go back to the Moody diagram, just glancing at this, those were the two factors that told us the friction factor here over on the left vertical axis. And so the two things that we were accounting for in the Moody diagram was here on the vertical axis on the right, relative roughness, and so some relationship of the material roughness to the pipe diameter. That was on the vertical axis, and then on the horizontal axis was the flow conditions expressed as Reynolds number. So those two things also show up here in the Colebrook equation. Now it's an empirical equation, and so there are going to be these strange numerical factors in here that just make the observed data fit with what we need it to be, and so 3.7, 2.51, there's no like units conversion that makes these factors any more sensible than they already are. Remember, Reynolds number is unitless, and then K sub s to d is also going to be a unitless ratio. And so make sure that when you express your relative roughness that both your K sub s and the pipe diameter d are in the same units. All right, so this is an implicit equation, and let's get some practice with that. First of all, we'll just set it up on the whiteboard, kind of a trial and error approach that then we can also solve on Excel using a manual trial and error, and then we'll also take a look at Goal-Seek, and then it's also possible to solve it on a calculator if you have the patience to type the formula into your equation writer. Okay, so the situation that's described here is that we have a certain pipe. It's 136 millimeter diameter, galvanized iron pipe. So if we go here to a table of equivalent sand roughness, you can see that galvanized iron has an equivalent sand roughness of 0.15 millimeters. And so that's where this data comes from. You've got that information in your text. And then we have a flow rate of 200 liters per second going through the pipe. Now, this is the typical kinematic viscosity for water at 20 degrees Celsius. And so let's try and calculate what we know so far that's going to go into that equation so that we'd be able to try and find out what's the F value we should use for this. So D is 0.136 meters. In other words, that's 136 millimeters, as it says on the screen there. The K sub s, 0.15 millimeters. And the flow rate that we have is 200 liters per second, and so that's 0.20 cubic meters per second. For this pipe diameter, let's calculate the cross-sectional area. So it's pi d squared, so pi times 0.136 meters squared divided by 4. Okay, so the cross-sectional area is 0.01453 square meters. And if we've got the cross-sectional area, we can find the flow velocity through the pipe. So flow velocity is Q divided by area. And so our flow rate is 0.20 cubic meters per second. And the cross-sectional area was 0.01453 square meters. And so the velocity through the pipe is 13.77 meters per second. So it's moving pretty quickly through that pipe. And with the flow velocity and the kinematic viscosity and the pipe diameter, we can now calculate the Reynolds number. And so the Reynolds number is the velocity, so 13.77 meters per second, multiplied by the pipe diameter, 0.136 meters, divided by 1 times 10 to the minus 6th meters squared per second. Okay, so that Reynolds number is 1,872,413. So this is just like the preliminary setup. Now what we need to do is try and find out if the left-hand side of the equation and the right-hand side of the equation are equal to each other. So just for those people who are following along at home, let me bring this up on the video. Okay, so we have to start with a guess. And so the guess that we'll start with is, what if f is 0.02? Then we're going to check what is the left-hand side of the equation and what is the right-hand side of the equation. So for the left-hand side of the equation, what that means is, what we want to have is 1 divided by the square root of f, 0.02. How many of you have calculators today? Basically everyone. Can you tell me what is the left-hand side of this equation for f is 0.02? So what's the square root? 1 divided by the square root of 0.02. 7.071, right? Okay, now the right-hand side, this is going to take a little bit more effort. So the right-hand side is -2 times the logarithm of k sub s. So that is 0.15 millimeters divided by 3.7 times the diameter, and we have to have the diameter expressed in terms of millimeters, so 136 millimeters, plus 2.51 divided by the Reynolds number, so that is 1,872,413 times the square root of our guess. You know, we're just checking to see, is it this guess value of 0.02. So the square root of 0.02. All right. So if you wouldn't mind, put that into your calculator. So we need to find out the two terms inside the Colebrook equation, then take the logarithm of it, and then multiply it by -2. What is it? 7.0. That's not quite what I got. Yeah, there might be. It's easy to make mistakes on these ones. No, I don't think that's it either. Hey, we have a winner. Third time's the charm. Yeah, I think it's 7.024. Now that just illustrates that it took us 3 times to get it right. You really need to be careful with these, and it's, you know, the mistakes will pop up for everyone at one point or another, so it's nothing to be ashamed of or have a bad feeling, other than just maybe double, triple check the calculations when it really counts. When it really counts is when you're building anything and on an exam, right? So, yeah. So the question is the left-hand side equal to the right-hand side? Well, it's pretty close, but it's not equal. And what we want is we want it to converge till it's totally equal. And so now what we can do is we can check some other value. So we don't know whether to make this f value guess larger or smaller, because we haven't done enough guesses to see if it's getting bigger or smaller, like relatively on the left and on the right. So what if our next guess was 0.01? Okay, rather than doing this on the whiteboard, one of the nice ways that we can iterate is with Microsoft Excel. Okay, so we have a k sub s in this case of 0.15 millimeters. Our diameter that's known is 136 millimeters. And the Reynolds number that we calculated is 1.87 times 10 to the 6th. All right. And let's just double check this guess that we had of 0.02. because we know what the left-hand side and the right-hand side is supposed to be. So that's a way for us to check if we type the formulas into the spreadsheet correctly. Okay, so the left-hand side of this is equals 1 divided by square root of f. Okay, so far so good. Let me actually show a little bit more precision there so that we can know for sure. Okay, now the right-hand side equals negative 2 times the logarithm of k sub s, so it's this cell, divided by 3.7 divided by d. I've just done something a little strange there because maybe you're more used to putting in a parentheses and multiplying it. Like the other way I could write this is I could say, let me see if I can make this a little bit bigger. Negative 2 times the logarithm of k sub s. You could also say, parentheses 3.7 times d, but it's actually fewer keystrokes if you just say k sub s divided by 3.7 divided by d. Algebraically, it's the same thing. So just maybe get used to that's how I type the Colebrook equation. Seems a little weird at first, but maybe you'll start doing the same thing. Okay, so we've got that first term in the Colebrook equation. Now the second term is plus the 2.51 divided by the Reynolds number divided by the square root of the f value. All right, so now if I've put all my parentheses in the right spot, this should be 7.024. Let's show a little bit more precision there. Okay, good. And now the difference between the two is going to tell us when we have an accurate match. And we're not there yet because we want the difference to be 0. That's how we know that our guess has converged on the right thing, on the right number. Now the typical range of f, like how far and wide should we be looking? F usually varies from 0.008 to 0.038. That's about every situation you'll encounter. The f value will be somewhere in there. So let me do this. Let me have it start 0.008, 0.009, 0.01. And then let's just go through this all the way to 0.038 and find out where is it closest. And so now I can, now that I've, I may need to anchor my references, right? I didn't anchor any cell references, so I'm fine there. Here, though, I need to reference that, put in my, how you can name cells? This cell right here, I've named that D. You can name this RE for Reynolds number, this K sub S. And so here in my formula, it's already translated where I clicked to the name of those variables rather than, like B3. So here it's saying K sub S, D, RE. It's because I named the cells. So don't get thrown off by that. But the point is that it's already anchored because of those names. So I don't need to put in the dollar signs because it's already anchored. So let me double click and this will go all the way down to the bottom. This will go all the way to the bottom, as will the difference. And what we're looking for is where is that difference minimized, and then that tells us it's the correct f value. Okay, so the crossover point is somewhere between 0.02 and 0.021. So what we could do is we could try and get a little bit closer. 205. Okay, already gone too far. 204. What we're looking for is we want that to be 0. 203. Yeah, that's about as good as we're going to get it, I think. Because if we go now to 202, yep, it's larger. Okay, so the f value, f equals 0.0203. That's the f value that makes the left-hand side and the right-hand side equal. That's how we do it by trial and error. Of course, rather than make this whole long row, of every conceivable f value, we could have just used goal seek or solver to do a similar thing. So remember that our k sub s value is 0.15 millimeters, the diameter is 136, our Reynolds number is 1.87 times 10 to the 6th. Right? Okay. So we just have to have some guess value, so 0.008, and then we'll solve the left-hand side, 1 divided by square root of f. So that's our left-hand side. Our right-hand side, negative 2 times the logarithm of k sub s divided by 3.7 divided by d plus 2.51 divided by the Reynolds number divided by the f value. All right, so now the difference is going to be one minus the other, and it honestly doesn't matter which, but what we're looking for is in goal seek, data, what if analysis, goal seek, we're going to have it set this cell to 0 by changing our guess value of f, and so it iterates that. That's a slightly different f value. I must have typed something in wrong. Let's see. Oh, yeah, good catch. Thank you. So it's the square root of f. That'd do it. All right. SQRT. All right. So now let's do that goal seek again. We want the difference to be 0 by changing our initial guess of f. And it rips through it. All right, that's more like it. That's what we're looking for. Now, the convergence criteria on goal seek is just set to a certain threshold. I think it's 0.001. Occasionally, you'll run into troubles where you can see that the left-hand side and the right-hand side aren't actually converged. And so there are some instances where you have to use solver instead of goal seek. But in this case, it worked just fine for us. I'll show you when it's time to switch over to solver rather than use goal seek. But for now, I don't think we're there. Any questions about using the spreadsheet to solve the Colebrook equation?
Are you going to make that available on Blackboard?
Make what?
The Excel file?
I can. I hadn't planned on it. I mean, I think it's the sort of thing that you'd get good practice typing it in yourself, creating it from scratch. But yeah, I will post that on Blackboard. Was there another question over here?
What level of precision should we usually look for?
I think that we don't usually bother reporting f value to any more precision than, no, that's too much. So let's see, 10th, 100th, 1000th, 10,000th. So this is plenty accurate. Okay, so that's the Colebrook equation, and it's always valid. There is also a way that you could put the Colebrook equation into your calculator and solve it using the solver, the numerical solver. I think most people here have Casio calculators because that's what you're encouraged to purchase when you're a freshman. But I wanted to show you, I mean, you already know how to put equations into the Casio calculator. And I have a video that I think walks you through the process of putting the Colebrook equation into the Casio. If I can, let me just double check. Let's see, so Casio, Colebrook equation. I may need to, we're going to watch this just now. I think I also have it posted how to do it with the Casio, but just for purposes of contrast, I'm going to make the suggestion that you might want to consider upgrading your calculator. The Casio has served you well. You've probably already gotten your $18 worth of value out of it. And I realize there's limits on the calculators they let you use on the FE exam, but there aren't limits on the calculator you're allowed to use for the rest of your career. And so sometimes your work is a reflection of your tools, and you can do your work more quickly if you have more sophisticated tools. And so I'm going to show you what I think is the best engineering calculator that's available. And just as an illustration of what it can do, there's an emulator that I downloaded that kind of allows me to demonstrate on the screen how you'd solve the Colebrook equation with that HP 50G calculator, which is the one that I think is the best one.
There's no such thing as a perfect writer. This is why I use Grammarly to check my work.
If I'm putting commas in the wrong places, that can shift my credibility and ability to influence and persuade others.
It helped me become a better writer and not be so afraid to share.
English is my second language, but I use Grammarly.
Let's see, I just want to make sure I'm getting audio. All right. All right, so equation writer, trial and error on the paper. You can use goal seek on Excel. You can do like a manual goal seek, row by row. However you want to solve it, the Colebrook equation, there's a lot of different ways. But if you really want to save time, what you can do is use an explicit equation rather than the implicit equation of Colebrook. The Jain equation is an approximation of the Colebrook equation that's only valid over a narrower range of conditions. If you happen to be working on a problem and the k sub s to d ratio is between negative 10 to the 6th and 10 to the minus 2, or a Reynolds number between 5,000 and 10 to the 8th, then you can use the Jain equation. And what you'll notice is that the f value is only on the left side of the equation. It's not on both sides of the equation. So it can be solved directly without the need to iterate. It's a lot easier to solve for f value with this Jain equation. So let me give you a few moments to try out the Jain equation. I'm going to pause, stop talking here, and ask you to see what is the f value in the situation that was described before. Let's see how closely the Jain equation approximates, and we are within that acceptable range of conditions. So the Jain equation, with any luck, should give us about the same answer as Colebrook did. Okay, I think it worked, right? You get essentially the same thing, 0.0203, as we calculated when we were using the other approaches with the Colebrook equation. Any questions about the Jain equation? Now you can use the Jain equation anytime this semester unless the problem explicitly tells you that you should use the Colebrook equation instead. So there may be a quiz or exam question where I want to just make sure that you know what the Colebrook equation is and how to utilize it, but otherwise you can feel free to use the Jain. Yeah?
So does that kind of negate the fact that it says that the KS over D ratio, we still have to take that into consideration, or do we just use it?
You should still check it, but that's a pretty wide range of applicability. I don't think we'll generally face questions this semester where we're not in that range. But that's a good point. You should still get in the habit of checking that, because error can arise if you're misapplying a formula. Are there other questions? Yeah?
So on homework problems, are we allowed to use Excel?
Mm-hmm. Yeah, you are. And so if you do use Excel on your homework, please be sure to upload the Excel file. And also, because you know you're going to be creating a PDF for the grader. And so include a printout of the spreadsheet, but then provide the file itself in case you've made a mistake and the grader needs to get in and take a look at what you've done. All right. One other approximation for estimating the f value is the Blasius equation. And it's only valid for a Reynolds number up to 100,000. So it's relatively simple. You can see it's a function of only the Reynolds number that the Blasius equation applies. So what would be the Blasius-derived F value for the previous case? Well, it shouldn't be exactly the same because in the previous case, our Reynolds number is too large. So maybe we won't even bother putting that in there because it doesn't matter what the Blasius equation would say because our Reynolds number in the previous example was 1.8 million and the Reynolds number here only goes up to 100,000. But it's another way of approximating the F value. Doesn't apply. It's outside of the Reynolds number. Okay, the rest of what we're going to talk about today is when you want to find out how big the pipe needs to be for a certain situation. The example that we worked on Thursday last week was we had some tank and we knew what the head loss was going to be. We knew essentially a situation where if you've got an elevation of a tank and you know where the building is and you know what the flow velocities are going to be, sometimes you know the expected head loss. That's always the case where you have a known elevated tank and a known location where you're piping water to. And so you'd know the expected head loss by finding the difference in the pressure head and the elevation head at one location and at the other. And this slide makes the notes. Sometimes we just omit the velocity head from these sorts of calculations because it's relatively small. Like if you look at the magnitude of the velocity head, there's just not that much energy there unless the water is moving extremely fast. But in the range of about 1 meter per second, the magnitude of energy in the velocity head, and especially in the velocity head difference, is probably negligible. So occasionally we'll just have the pressure head and the elevation head for estimating the expected head loss. In situations like this, sometimes we know how much water is needed at a certain location, and so in the case of some building on a hill, maybe you know how much water is needed there because you know what the number of people are going to be, and you have some sort of a guess of what their water consumption patterns are, and you know the time of day that the most number of people will be in the building, and so you've gone through some sort of analysis that tells you the Q, and the pipe diameter that's required has to be designed to match the conditions, and so you want to make the pipe small enough that you save money, and if you make the pipe too big, then you'll still have enough pressure at this downstream location. Making the pipe larger can still deliver the required pressure, but it's not economical. And so the kind of the design juggling process that you're going through is checking to make sure there's not too much head loss, and if there is too much head loss because of an undersized pipe, then that means that you haven't delivered enough pressure to the downstream location. But if the pipe is too large, you have satisfied the downstream pressure that's required, but you're spending too much on that large pipe. So this process tells you to match the required pipe size to the allowable head loss for a certain flow rate. And the difference between design and analysis is in the case of analysis, you're just finding out how much of something there is, or like what will be the pressure in a certain scenario, whereas design is iterative and you're having to optimize. And the optimum solution is one that just barely meets the requirements. The Darcy-Weisbach equation, if we have the unknown becoming the pipe diameter, we could rearrange the Darcy-Weisbach equation to look like this. For a circular pipe where we're trying to solve for some unknown pipe diameter, this is what the Darcy-Weisbach equation looks like. Now the tricky thing about it though is we can't just solve directly. This isn't going to be a one-step calculation to find out how big the pipe should be. Like even if we did know the flow rate, maybe it's 100 liters per second. And even if we did know the allowable head loss, 3 meters of head loss, the thing that we don't know right off the bat is going to be the F value. Because remember, the F value depends on not only just the flow rate, but it also depends on the diameter of the pipe itself. Because if you have a small diameter pipe, then the velocity is high, and the Reynolds number is going to be high. And so we can't just solve this a single time and know what pipe diameter is required because of the F value. Even if we use the Jain equation to solve for the F value, we're still going to have this problem of needing to iterate this and solve it over and over again. And so I'm going to show you the process that you go through, the step-by-step procedure to find out what's the required pipe diameter for a certain scenario. The accurate approach, that's a little bit more difficult because it requires us to iterate, uses this process. The first thing you do when you have too many unknowns is you make a guess. And you solve the entire process with your guess, and then you check to see whether your guess was correct. And then if your guess wasn't correct, you do the whole thing over again with a different guess. That sounds tedious, right? Luckily, we've got Excel. It takes the sting out of it. Okay, so you assume some F value, because everything else in here is going to be known. 8 is a constant. The length of the pipe will be given. The required flow rate will be known. The head loss and G and pi, all of those are known, but our two unknowns is what diameter of the pipe is needed and the friction factor. Who can restate why we don't know the F value? Even if we know the pipe type, like even if we know say it's cast iron, because we don't know the diameter. Exactly right. We don't know F until we know the diameter. So that's why we've got two unknowns. And they're interrelated, fortunately. F depends on D, and D depends on F. And so eventually, we can get the solution to converge because they're related. It's just that right off the bat, we don't know what the diameter is. So we make some guess, and we solve what would be the D value if that was the F. And then you say, all right, for that D value, now I know what the velocity through the pipe is going to be, so that allows you to calculate the Reynolds number. And then we go through the steps of checking the F value. For the new Reynolds number that you know, and for the equivalent, for the relative roughness, you calculate a new F value either with Colebrook or Jain, and then you check, how does this new F value compare to your original guess? And if there's an error, then what you do is you'd use this newly updated F value, you'd move that up to the top, and you do the whole thing over again with your improved value of F. And we keep doing it until F isn't changing anymore. So we keep going through the process until convergence. And that's what we call when the F value is stabilized and the diameter estimates aren't changing anymore. Okay, so let's practice this approach. For a length of 40 meters, what diameter of cast iron pipe is required to achieve 300 liters per second? So we're going to find some diameter of pipe needed to take the water from like a mainline pipe through this lateral to a location where we're going to have a head loss of 45 meters between the two, and the flow rate is 300 liters per second. What happens if our guess is too small? Like what if we undersize the pipe? What's going to be the implication of that? What if the pipe's too small? Like of these things that I told you, length, flow rate, cast iron, if the pipe is smaller than it needs to be, what would be the physical side effect? It wouldn't get enough, well, you're close, because this is, it's just discharging it to an open valve. If it was enclosed, it would be not enough pressure. But here it's going from whatever the pressure is to 0. And so the pressure gradient's going to be the same, but it's the flow rate wouldn't be high enough. So it's just like if you are trying to fill a pool with a garden hose rather than trying to fill a pool with a firefighting hose. If the hose is too small, you've got all of this pressure trying to drive the flow through a really small diameter, and you just can't achieve the same flow rate as you'd be able to get if the pipe diameter was larger. All right, so we're going to go through the process of finding out what diameter is required to achieve 300 liters per second. Now we start off with a guess of the F value, and let's go through this manually one time. and then we'll move it over to Excel just to illustrate how we can kind of automate this process and make it a lot easier. Okay, so we have some assumed F value. Now the problem says that we've got cast iron pipe, and so K sub S is 0.26 millimeters. The length of the pipe is 40 meters, and the flow rate is 0.30 cubic meters per second, and H sub F is 45 meters. Okay, so let's try let F equals 0.015, just as a starting point. Okay, so our diameter is going to be 8 times the pipe length of 40 meters times the flow rate of 0.30 cubic meters per second, and we have to square the flow rate, divided by 45 meters, which is our head loss, times G, 9.81 meters per second squared, times pi squared, and then we multiply all of that by our guess of the F value, 0.015, and take it to the 1/5 power. Okay? And you've all got calculators, and so why don't you put that into your calculator and tell me, for the guess value of F, if this was our roughness, then what is the diameter that's required for this pipe? Good, that's right. 0.158 meters. So if that was the diameter of the pipe based on this guess F value, then what we can do is we can also calculate the cross-sectional area that arises out of this diameter. And if we know the cross-sectional area, then we can find out what the velocity of flow through the pipe would be. All of these things kind of cascade from the initial guess of the F value. And so if we've got the diameter, the velocity of the water flow, and we know the kinematic viscosity of water, then we can also calculate the Reynolds number. And now with the Reynolds number, we know enough to check and see, is our guess correct? You know, do we have this correct F value? And so we'd use the Jain. So use Jain to check F. Okay, so the newly updated F value is going to be 1.325 divided by the natural log of K sub S to D, so that's 0.26 millimeters divided by 3.7 times the diameter of this pipe is 158.2 millimeters. And then the second term in the Jain equation, 5.74 divided by the Reynolds number to the 0.9 power. And the Reynolds number we have up on the screen there, 2.414 times 10 to the 6th. And we take that to the 0.9 power. And then all of that is squared down in the denominator. Okay. Now it turns out that when we use the Jain equation to find out what would be the F value, it's actually 0.0224. So we have a problem. The problem is that this F value doesn't match our initial guess. Our initial guess was maybe the F value is 0.015. But then when we ran all the calculations, we found the diameter that would arise out of that. And if we have a certain diameter, we have a certain flow rate, and that certain flow rate gives us a Reynolds number, and so on and so forth. All of the factors that do account for the energy loss, we find out that the F value between the assumption and the updated F value don't match. So what that means is we have to start at the beginning again, and so instead of having 0.015, we use this new guess. Let's see, what is it at 0.0224? And so we're going to have to solve everything again using this new F value of 0.0224. We replace the old F value. And so rather than do that on paper or on the whiteboard, let me show you how we can follow the same process using a spreadsheet. Any questions before we do this second round of iteration? Okay, so our flow rate was 0.3 cubic meters per second. The K sub S for this pipe is in terms of meters, because I'm going to want everything to be in consistent units. I either have to do this in millimeters and the pipe diameter in millimeters, or I'll just do this in meters. And so it's 0.00026. The length of the pipe is 40 meters. G is 9.81. The H sub F is 45 meters of head loss. And then the kinematic viscosity of water is 1 times 10 to the minus 6th. All right, so assume an F. We've already been through this process once, but let's double check by starting with our very first guess. It was 0.015. We just pull some number that's in the acceptable range out of the air. All right, so now we calculate the diameter based on that. So it's equals 8 times the length. I'm going to anchor that reference, times the flow rate squared. Anchor that and square it. Times the F value divided by H sub F times G times pi squared, and then all of that is to the power of 1/5 power. Okay, so 0.1582. That's what we know from before is the correct diameter that will arise out of this F value. Okay, so then for a certain flow rate, the flow conditions are known, the flow rate is known, the cross-sectional area would be pi times d squared divided by 4. Now the velocity is just q divided by the area. Okay, so 15.26 is the velocity. And the Reynolds number is going to be the velocity times the diameter divided by the kinematic viscosity of water, which was up here. I'm going to anchor that reference. I'm intentionally not anchoring all the rest because I'm going to kind of copy and paste this over and over again until it converges, rather than having to type the formulas many different times. Okay, so the new F value I'll calculate with the Jain equation. 1.325 divided by the natural log of K sub S divided by D. So K sub S divided by 3.7 divided by the diameter that we determined here, plus 5.74 divided by the Reynolds number to the 0.9 power. and then all of that is squared in the denominator. Okay, we have this updated f value, and it matches what we've got on the whiteboard. All right, now this is where the fun begins, where we don't have to type any more equations, and we get the benefit of Excel repeating things. So iteration 2, I'm just going to use this updated f value for the second time around because my difference is too big. Like if we compare the new f value minus the old f value, and then we divide it by the new and multiply it by 100. So divided by the new times 100. My percent change was 32%. I'd like it to be in the range of 1% difference, meaning that it's converged and it's not changing anymore. So for phase 2 of this iteration, my new f value would just be the guess from before. Now what I can do here is I can just copy this cell, and it's going to paste the formula. So Control C and then Control V to paste, and all of these references up to the preliminary stuff, that's staying the same. Let's see, what wasn't anchored was the reference to the f value. Everything else is constants that I don't want it to be adjusting. So we have now a new diameter. So determine the flow conditions. I'm just going to copy all of this, Control C, Control V. So now something's not right. Maybe it didn't copy over the flow rate for whatever reason. So the flow rate is, all right, that's better. All right, so we have an updated velocity, and we've got an updated Reynolds number, and so now we can get the new f value and the new percent difference. And so I'll just highlight those cells, Control C, and Control V to paste them. I think I probably didn't anchor something that needed to be anchored up above, so let's look at that. Because my f value went crazy. Didn't do what it should do. The error isn't jumping out at me. Case of S. Let's see. Oh, I think you're right. So this should be looking up here at the case of S. Thank you. And so let me change that in the formula. All right. All right, that's more in the range of what we'd expect. And what you'll notice is that the new updated guess is pretty close to the previous guess, and so it's converging very quickly. We'll do an iteration 3 just because it's simple, but from a percent difference standpoint, the input and the output f values are pretty close together. Let me just copy all of this. I'm going to do this whole iteration, Control C and Control V, and I need to change this f value, though, to be from the previous guess. And so this new input of iteration 3 is the output of iteration 2. And so we get some new diameter. The flow rate, for whatever reason, just isn't copying right. Let's just force that to know the flow rate, and we get a new velocity, Reynolds number, f value. Okay, so the input f value and the output f value are very close together. The percent difference in change of the f value is less than 1%. And if you look at the diameter, we said it should be 0.1707, and the previous iteration we said it's 0.1714. So, I mean, it's easy enough just to copy and paste it again and see, just to make sure that it's stabilizing. Control C. Control, let me get all of it. Okay, and then the input is the output of the previous iteration, and the flow rate, 0.03. 1707 is the diameter, 1707. So the solution is converged. The F value isn't changing anymore, neither is the diameter. So that's essentially the more accurate, but because it requires iteration, more lengthy approach. There's an empirical equation that shortcuts the need to go through this process of guessing and checking, and then always updating along the way. I'll show you that equation here in just a minute, but are there any questions on the method that we used?
So would goal-seek not be accurate enough to do the excell method?
Good question. I'm glad you asked that. Yeah, so what about goal-seek? How would we, if we were going to use goal-seek, I think the reason why we can't do it in a single step, like we couldn't just say, like what is the goal?
The percent
So,
difference would be set to
yeah.
whatever you were
Well, let's give it a shot. I think that it won't work because two things are changing simultaneously, but let's see, data, what if analysis, goal seek. Our difference is 0 by changing this input here. All right. Oh, actually, it worked pretty good. 1707. Yet, there's sometimes are cases where goal seek won't work because at the same time that you're changing the F value, the amount of head loss is also changing. But I guess in this case, the head loss is just known from the beginning, the amount of head loss. So yeah, good call on checking the goal seek. For the homework problem that is related to this, I'd like to see you going through the process of copying and pasting on the spreadsheet, like the iteration rather than the goal seek. Because for one thing, when you do a goal seek, you can't see like the process because it just shows the final answer in the screen. So I think that you've got a homework problem where you're having to find the required pipe diameter, and where you do make it this method of assuming an F value and then repeating. But great question. I'm glad you asked that. Are there other questions related to this process? Okay, so here's the other equation, the so-called easy method for finding out the required pipe diameter. And you can see I put easy in quotes because the formula is really complicated and there's just tons of opportunities there to make a calculation mistake solving this equation. But since we've got the time, I want to see if we can get a sense for how accurate this diameter is for the previous problem that we just solved. So let's find out for the problem we're talking about. The Q is 0.3 cubic meters per second. The H sub F, 45 meters. The pipe length, 40 meters. And then the K sub S, 0.26 millimeters. So we've got all the data we need. And by the way, you need to express all of these in their base units. And so K sub S should be meters. Length should be meters. Q, cubic meters per second. H sub F, meters. So be sure that you change the K sub S to meters and don't just have it in millimeters. So in other words, the K sub S is 0.00026, 0.00026 meters. All right, see if you can get this formula to work for you. And what we're looking for, the previous example, when we did it on the spreadsheet, we got that the pipe diameter was D, 0.1707 meters. Do you have a question?
Yeah, do you want us to use 1/10 centimeters for the, is that the kinematic viscosity?
It is, yeah, that's kinematic viscosity here. And so use 1 times 10 to the minus 6th meters squared per second for that. Okay, so it gets us most of the way there. You know, it's better than a ballpark estimate, but it's not as tight as, say, the agreement between Jain and Colebrook was, where earlier today those were in virtual agreement, you know, down to the thousandth. In this case, where we know from the more accurate iterative approach that the pipe diameter is 0.1707 meters. This tells us it's 0.175, but you know, in a way it may not matter because you can't go out and find a store that is selling pipe diameter 0.1707. You're restricted to commercially available pipes. And so this tells you the required diameter, and so what you'd do is you'd find what's the next standard size diameter larger than that. And so it may be a 200 millimeter diameter pipe would probably be the commercial size variation. You know, 175 millimeter would be too small. No, 175 would be fine, right? Okay, yeah. So 175 millimeter would be the probably, depending on the parts availability, where the project is being conducted. But you can see that this explicit approach saves you the trouble of having to use Excel. Okay, well that's all I have for you today. Let's take one last look at these announcements. Remember that your next homework assignment is due a week from today, and we won't meet in class on Thursday because of the Winter Technical Conference. But I will be in my office during my normal office hours, so that if you have questions, please feel free to stop by.